Before we begin, I'd like to acknowledge my co-authors on this paper from Ducks Unlimited who have provided intellectual guidance throughout the duration of the project, and also a variety of folks and organizations that have contributed substantially to their work and whose help the project would never have happened. Okay, let's talk about the status of ducks for a second, and we're going to focus on the western boreal forest, and then we'll taper down a little bit to the oil sands region or the surrounding area. The numbers you see here under long-term average are the population level goals that are set by the North American Waterfowl Management Plan. So these are targets for conservation that we're seeking to achieve. And if we focus on this bottom row for a second here, we see that there's about 10.5 million ducks in the boreal forest, in the western boreal forest in particular, and on average they're doing pretty good. But this doing pretty good statement is sort of hiding for the fact that the reason they're doing pretty good is that some species depicted here in green are increasing quite dramatically, 40 to 50%, while other species depicted here in the red are decreasing quite a bit. And so we're seeing a change in community composition in the western boreal forest related to the different species of ducks. And so the question is about why is this happening? The oil sands area contains about 12% of these ducks, and the population trends in that area mimic what I show here for this region as a whole. Okay, when we talk about what makes populations of ducks go up and down, we do have some information on that, and where we have that information suggests that about 90% of the population trajectory is driven by what's happening on the breeding grounds themselves. We heard a few statements in the past few talks about, keep in mind what's happening on the non-breeding areas, but what we know for ducks is that most of what drives populations is due to the breeding grounds, and it gives us cause for some concern or some wanting us to pay attention to what's happening on their breeding grounds in terms of these landscape changes and what it might mean for waterfowl. Okay, we know there's lots of landscape changes, so I'm not going to spend much time on this, but if we focus on just the industrial infrastructure, the local scale effects right now, when we look at it at a broad spatial scale across the boreal forest, we see that, they're depicted here in red, we see that a lot of it is concentrated in the southern regions of the boreal forest. And why is that important for ducks? Well, this map here shows the distribution of ducks, generally speaking, with the highest densities shown in the red and the yellow. And we see that there's a pretty good spatial overlap between the places where we have the highest industrial development and places where we tend to see the highest densities of ducks. Okay, so why is this a problem? Well, I guess it's a well-known fact that ducks like water, and in this part of the boreal forest, there's a tremendous amount of wetlands there. These are both open water systems and peatland systems. And as Kelman talked about earlier, these systems are really important for movement of water in the landscape. And in fact, we know that peatlands play an important role in the transfer of water nutrients from various parts of the landscape into some of these open water systems used by ducks. And we think that is this interconnectivity of the sort of the closed peatland systems and the open water systems used by ducks that might make them sensitive to landscape change. And so just a brief example of what I mean by that is that here's a picture of a fen. If you go out on the ground, you put your hand down, it's wet, you know it's wet. But if you go a little bit higher up in space, or up in the air, we see that some of these things are very linear in their format, these fens. They're transporting water a long ways. And some people call them the green rivers of the boreal forest. And some long ways could be many, many kilometers. And as you can see by this sort of island here, you can see there's a direction of flow. So it gives you evidence that there are some cases long distance transport of water and nutrients across the landscape, but there are also short distance transport between those systems, as I mentioned earlier. And so one of the things that we're really concerned about is that perhaps if you build a road across some of these flowing systems, that this causes some hydrological impairment and that there's a net loss in habitat quality from a duck's perspective. But the other thing we're concerned about here is a lot of the linear features on the landscape that are depicted in red. And as you can see, there's in some places there's a tremendous amount of them, and they do a pretty good job of connecting the dots between wetland systems. So these wetlands are shown here in blue, and a lot of these linear features go from wetland to wetland. And we believe this can increase the permeability of this landscape to predators of ducks. And so the issue that we're concerned about is that we know that when we have habitat fragmentation, we've already seen increasing numbers of crows and ravens in this landscape, but we also think that there could be positive responses of predators. And so we have these two hypotheses about upland fragmentation and wetland or hydrological impairment that we are concerned about investigating. Now, we don't really know at this point in time which one, if any of those two hypotheses are operant in this landscape, but what we do know here is that we have this again, repeating the image of red for anthropogenic disturbance, places where there are a lot of anthropogenic disturbances, we also see that there are negative population trends, and that's depicted here in the red. And so there's this big spatial overlap, this big sort of fingerprint of human development and negative population trends. And this is some work that we're currently writing up. And so that made us ask the question that I'm going to talk about today is, what are the relationships between roads, pipelines, and seismic lines and populations of ducks in the boreal plains, specifically in Alberta and BC? Now, the operant hypotheses that a lot of conservation and management efforts in the boreal forest use currently are that as the amount of habitat change increases, the number of pairs of ducks that choose to settle on the landscape or their breeding success declines. That's a pretty basic statement, and then the issue is we don't have a lot of information about ducks in this landscape. It's a place that's been very poorly studied from a duck perspective, and so we don't really know which of the many landscape changes that are out there are important for ducks. But the other piece that's pretty critical if you're trying to design a management program is what are underlying biological mechanisms, because your management programs need to target the appropriate mechanisms in order to be successful. And so these are the two questions that we're going to try and get at here. And I'm going to focus on that second question. Now, these hypotheses are not mutually exclusive, but we think that the relative patterns between the pair settling and their success can tell us something about which one of these mechanisms might be operating on the landscape. And I'll walk you through that. And then when I'm doing this, I'm going to show a minus sign here for what I'm depicting as a negative relationship and a 0 for what I'm depicting as a neutral relationship. And a negative relationship is that fewer birds, higher densities of linear features. Okay. So the bottom-up hypothesis is really a wetland quality hypothesis. We predict that there's less food available in places that have higher densities of linear features for the reasons I mentioned earlier. The ducks are really good at sampling their landscape, and they know when there's not a lot of food on the landscape, and so we predict that they would avoid those landscapes that have been impacted by linear features because of less food availability. Their breeding success is a little bit harder to predict because it depends upon how many ducks are there and what's the per capita food availability and things like that. So that's a little bit harder to predict. From the top-down hypothesis, this is really, again, a predator hypothesis. It's about increasing the risk that you or your nest will get or your ducklings will get eaten when you're there on the landscape. And so we don't know a lot about the ability of birds to detect predation risk, to assess predation risk in the landscape. And so that sort of spawns two different sub-hypotheses. The first hypothesis is what we're calling a sink hypothesis, and that's birds can't detect risk on the landscape. And so they settle on these landscapes in equal abundances as to less disturbed landscapes. However, because they're higher risk of predation, they do poorly. Their nest success is lower. The other hypothesis is that birds actually can assess risk in this landscape, and so they avoid that landscape, but not all of them do for whatever reasons. And those that choose to settle in these areas, they experience poor nesting success. So those are the sort of the relationships that we're going to be looking for in our data. We're going to take this 2 steps further. The next step is that, as I mentioned, the hydrological impact hypothesis really is predicated on the assumption that roads have a much larger effect on hydrology than seismic lines do. And so therefore we predict that if the bottom-up hypothesis is the most important hypothesis, that we're going to see this relationships where roads have a high level of impact, seismic lines have the least. However, on this sort of predation clade of hypotheses, it's more easily to envision that roads, pipelines, and seismic lines will have more equal effects on birds. But the third level that we're going to take this down to when we're assessing our data is that different species, depending upon where they choose to nest, may have different sensitivities to the different forms of landscape changes. And I'm going to depict that here by this table, which basically says, on the bottom-up hypothesis, birds are generally eating the same thing. We think if food availability is low, they're going to have equal response to linear features effects. However, on the top-down hypothesis, we don't think that we think that the predators that are changing in this landscape based upon literature and other information are predators that have the greatest access to ground nesting species. They're not species that are necessarily going to go swimming in the water to go get nests that are built over water, and they're certainly not species that are going to kind of crack open a tree or climb through a hole in a tree where a cavity nesting duck is nesting. And so we feel that they have the greatest access to the ground nesting species, and therefore we predict that if we see any changes, we're going to likely see the greatest effects will likely be seen in the ground nesting species. So those are the a priori hypotheses that we went into. This is what we're going to look for in our data. Study site was in, we have a primary study site in the oil sands region, a few secondary study sites around the area. And so what we did is we used a sort of classic dose response type of research where we sampled a bunch of spots where either there was no disturbance, low, moderate to high disturbance levels. And the two spatial scales that we're going to look at are the landscape scale, which I might refer to as grid scale on occasionally, 2.5 by 2.5 square kilometer grid that we sampled. And the other spatial scale that we'll look at is the wetland scale. So within those grids there are wetlands, and there are, we buffer the wetlands by about 300 meters to calculate the densities of linear features and so on in there. Basic field protocols, as you probably guessed, we use helicopters to go out there and sample all the birds that are on the water, so not just ducks, but also loons and grebes and other species. We're using some techniques to account for the fact that the detection of these birds is not perfect, and so we're using some techniques to correct for that. And then we collect some other data that will help us in our analyses as well while we're there, or from high-resolution imagery. Okay, and the basic statistical approach that we're using is we're saying, okay, we want to look at both settling, which is the pair count, and breeding success, which we're defining as a brood to pair ratio. It's the number of broods per pair. And we're going to do this, separate these into nesting guilds, and we're going to use techniques, a technique called hierarchical models that allow us to simultaneously correct for the sampling errors that we induce by being out there and being not perfect beasts and counting ducks. We're also going to use the technique will allow us to correct for variation in abundance due to the habitat types, because we know that habitat types have an important role in terms of the number of ducks that are there. So we're correcting for those two things and giving us a better ability to robustly assess the type of linear feature, the density of linear feature, but also the distance to the linear feature. And this one we'll only do at the wetland level, so the center of the wetland to the closest linear feature. So those are the three things that we're going to look at. We sampled, couple hundred, many hundreds of grids, thousands of wetlands, and counted thousands of birds. And when you're done with those analyses, for the non-zero relationships, you can make a bunch of graphs that look like this example here, and where we have on the x-axis we have distance to the nearest road in this case, and on the y-axis we have the response of the birds. And then what we did is, in this sort of preliminary results that I'm going to show you here, is we said, okay, let's calculate the percent change in those values, in terms of those duck values, as you go across that gradient. And in this example here, we get about 129% change in abundance as you go towards closer to the road. Okay, so now I'm going to do two things. The first thing I'm going to do is I'm going to show you the general patterns of relationships. And we're going to ignore the magnitude. It's just to give you an idea, generally are they increasing relative to linear features, or are they generally decreasing, or are they neutral? So we'll give you that first, and then we'll talk about magnitude. Okay, this is what we found for distance to linear features, distance to roads. And the table that it's set up is, you can see feature, parameter, and then the different nesting guilds. And the thing that's sort of the first take home here is that from a settling perspective, the only thing that we observe distance to linear features was for pipelines and roads for cavern nesting species, which means that those birds, those two guilds of ducks, settled in lower numbers as they approached the wetlands. So you might interpret that potentially as they may have been avoiding those wetlands. That's a bit of a stretch at this point in the analysis. The other point that I'd like you to take home from this is that the breeding success was potentially affected by distance to roads and also seismic lines. Seismic lines had a pretty consistent effect across the board. But the other thing that I'd like you to get from this is that for the ground nesting species, that breeding success was potentially impacted, or the relationship was negative for all the different linear feature types. Okay. The other point that you may have picked up from that graph that I showed was that when we stepped back and looked at these relationships where there was something going on there with distance to roads, most of those relationships happen in the last 200 meters as you approach the road. So it means that as you go beyond 200 meters, the line was pretty flat, but as you approach 200 meters, the line started to really taper off. And that was a consistent pattern for all those road effects. Okay, so let's look at settling patterns. And now we're going to talk about the density of the linear features at this point in time, as opposed to the distance that we just talked about. Two spatial scales again. I'm not going to spend a lot of time on this because, contrary to predictions, we didn't see any relationships with negative relationships with linear features at all. In fact, we saw some positive relationships. So I'm not going to spend a lot of time on that. But breeding success was a very different story. When we look at the two different spatial scales, the things that immediately popped out in the preliminary analyses here are that roads at the wetland level had consistent negative relationships across all the guilds, And the other pattern is that the ground nesting guild had a consistent negative relationship across all the different linear feature types. So now we've got two different things going on in terms of these ground nesting species. The distance to linear features has a negative effect on productivity, or negative relationship with productivity, and the same is true for the density of the linear features. Okay, so now I was struggling for how to now portray the magnitude of those different relationships in a way that was quick and easy and meaningful to folks. And so what I've done is I'm going to show a series of graphs now where on the x-axis we have the different linear feature types. On the y-axis we have the percent change in the values of either pair settling or breeding success. And as I go through these, I'll just ask you now just to focus on the breeding success bars, because as I've shown already, the pair settling, there's pretty much neutral or positive relationships, so we're not going to worry about that at the moment. Okay, here's the graph for cavity nesting guilds. We see that the largest percent change on average was seen for seismic lines. For overwater nesters, the largest percent change in breeding success was again due to seismic lines, very, very dramatic. But for ground nesters, the relationships between the percent changes associated with all the different linear features were approximately the same. Okay, so if we now sort of step back and put all these different pieces together here very quickly, it appears that nothing is happening with the cavity nesters. There appears that nothing, according to the negative relationships I'm referring, is happening with overwater nesters, but there appears to be something clearly going on with the ground nesting species. And if you recall the original prediction matrix that I presented here, that's most consistent with this top-down habitat sink hypothesis, and believe that that's evidence for potentially for increased predation of the ground nesting birds. Furthermore, if you recall the other predictions that we made about the relative importance of these different linear features, helping us identify which one of these hypotheses are operant, we did not see that roads had the greatest effect on the breeding success or the settling of birds. This wasn't supported. More so, I think we have greater evidence to support this other angle of roads, pipelines, and seismic lines having equal, or at least seismic lines having greater effect than the other two, which was not what we predicted. So to just give you some preliminary speculations based upon preliminary data analyses, what might these features mean for ducks? Well, there's potentially, in some cases, maybe preferential settling of these birds in areas of higher linear feature densities for reasons I don't know why. But in some cases, in some guilds, they may be avoiding regions that are within 200 meters of those linear features. From a breeding success perspective, tended to be reduced at higher densities or closer to linear features, particularly for that ground nesting guild. And seismic lines had strongest negative relationships on average across guilds. And we feel that these results are most consistent with some form of predation hypothesis, as I mentioned earlier, either an ecological sink hypothesis, or given that some birds may be preferentially nesting in these areas of high linear feature densities, an ecological trap hypothesis. And so the early recommendation, or early thing that we need to think about if we're developing a waterfowl monitoring program in the oil sands region is that you can't just count the number of adults that are out there in the landscape, because that's not telling you the whole story. A successful program likely has to adequately monitor breeding success as well.